reaction, just by looking at the two reactants, right, you should have been able to predict those were what kind of reactions. Double replacement, because you can see the ions of these salts, and those salts, that's just a really generic name for anything ionic. And you can kind of see, if you write water, how HOH, that it technically contains two ions, which is why water is amphoteric, because it has technically it has an H plus ion and a hydroxide. So I'm going to clear up some things first. I did see some questions on your problem set, so if I can clear up some of those, you guys can add to your pieces of your problem set, and you have the questions right in front of you. Most of you guys got 10 out of 10 unless you just neglected to try the questions, right? Chemists try. So try those out the best you possibly can. And I had a couple people stay for tutoring. They got the whole thing done with me in tutoring. So try. Okay, try to come to tutoring as well. Oh, and then I did have a, you know me, hold on. Gotta have those jokes. Hey, Litmus. Lesser blue. Okay, great. You guys are. Yeah, thanks. I try. All right, so before we get too far into the depths of reviewing our problem set, let's add just a couple of notes to our page. I don't remember what page it is, page 11 or something, which is your acid-base reactions. Yeah, so it's called, right at the page from us, it's called acid-base reactions. You already actually know both of them, so they're just simply double replacement reactions. So I just would like to do a couple of examples with you. So I should see you guys pulling up your books, and it's going to be the free space. And we're going to do a couple of additional reaction examples together, because then I think that very much may help you finish up your lab successfully. It's a pretty easy lab to get a 100 on. So what's the word neutralization just really mean to you guys? So that's what I was hoping I was here so I could actually help out with that. So neutralization is a process, where neutral is a characteristic. So what does neutral mean? What's it mean for pH? It means pH 7, right? So the word neutral generally means pH 7 or Switzerland, right? So it's a behavior. Oh, it is writing. Okay, good. All right. So the word neutralization is representing how we got that way, how we get to this characteristic. It is a process. It is the process of something neutralizing something else. So like if we neutralize a threat, we get rid of it. Okay, but in acids and bases, we're talking about something that is acidic in nature and basic in nature can counteract each other to make something that is supposedly neutral. However, not every single time will this compound, which is the salt, and when it's mixed with water, it kind of makes a solution. Not every single time is that going to actually be neutral. So your job that you just actually kind of explored today was when you mixed a salt with water, what was approximately the pH? Which salt, when mixed with water, led to a pH of neutral? Look at your data. You guys have your data in front of you. Okay, so let's look at the couple of salts you guys did. Sodium chloride, what happened with the litmus paper? What happened to the red litmus paper? Stayed the same, okay. So sodium chloride, you notice I'm writing the name out so you guys can do your own formulas, okay? Okay, what's up? You can start pulling some of those together, yeah. They're right here in front of it, okay? Grab them out of my room, yeah. So red litmus paper and blue litmus paper. And what happened to red? No change, okay? What happened to blue? No change. So overall, since it didn't change blue and it didn't change red, what's it trying to tell you? Back. Yes, it's trying to tell you it's a neutral salt. Okay, so we'll talk about why that is in a second. What was the second salt? Sodium carbonate. Okay, so for sodium carbonate, what happened with your red and blue? Red didn't change? Anybody? Did it change? So what happened to the red litmus paper? You should have written this down. Did anybody write this down? Did anybody? Zach's the only one that says it turned blue. Okay, so Brandon? It should have turned blue. Write this down if you didn't. You should have written this down for your own sake. Because how else are you going to determine if it's acidic, basic, or neutral? Okay, guys, what happened to the red litmus paper? I mean the blue litmus paper, stay the same. So I got one group that's going to be giving me good results. I hope the rest of you guys remember. So your job's conclude what that means in a second. Sodium acetate. What you got for me? What happened to the red litmus paper? Started to change kind of what? Bluey purple color, so it's still trying to change. It's not continuing to stay red, so it changed kind of bluish. Okay. What about the red? I mean, what about the blue litmus paper? Anybody? Did it turn reddish? Yeah, it wasn't this one. Can I get a conclusive remark on this one?
No.
Did not change. Okay. So no change with blue, and then ammonium chloride. What happened to red litmus paper? It stayed red. Okay. And then what happened to the blue litmus paper? Say again? Turned pinkish red. If there was a hint of a change, I'm going to say it probably did change. Okay. So red didn't change, so red stayed red, and blue turned red. Right, so from the data, you should be able to determine on the last column acidic, basic, or neutral. Okay? And so the whole idea here is that we can start to neutralize each other. We can start to neutralize things as a process. However, it won't always be pH 7. It will be in the realm of it, but it still can be a little bit maybe high, so like pH 8 or 9, or pH 5 or 6. It's just getting closer to neutral. Okay. So the way that you will always write these is if you continue to see the H and see the OH, you'll notice how the H with a plus charge will combine with the OH of the negative charge to make what? HOH, which we'll call water. And you don't write the X first, you always write the Y first because you write the cation first and then the anion second whenever you're writing your salt. Remember, cation, anion. So that's our general flow. So whenever you're looking at it from the particulate matter perspective, you can see that all your ions start to combine. So if I ever ask you to draw a particulate diagram, or basically notice what's happening, what are you noticing is happening? Actually, no, I have to show you another diagram. What you'll notice is that some of the OHs, which is a two-part, like that's an OH right there, will combine with an H plus to make water. You can see the Mickey Mouse kind of format there. Put your phone away, Frank. Okay, so go ahead and write out, let's do 2 of these. Write out this reaction in your book, and then write out this reaction in your book. Talk in your groups as you go, probably only be about 2 minutes. Write this out in your book. Brandon, what's the first reactant here?
HCl.
H and Cl. Megan, what's the second reactant here? So close. Okay, this is where we get that bi little word that comes back. Does anybody remember what the bi means? Yeah. Does mean there's a hydrogen with the carbonate. So this means there's a hydrogen ion with the carbonate, which is what you said was CO3 2 minus, right? Combine that together, what do you get?
You get HCl3.
1 minus, right? Because that 2 and the 1 plus combined to be a 1 minus. So instead, we'll write Na plus, right? And then crisscross that with HCO3, 1 minus. And I'll even put parentheses around it so you can see the distinct differences there. So Meredith, give me one of the products. So the H plus, when I can't make.
Sorry, H and then HCO3.
So how do I put H and HCO3 together? I don't want to write HH. I'll write H2. H2CO3, because instead of writing H and H separately, I'm just going to combine them. So that's, what's the name of that? Carbonic acid, right, that's carbonic acid. And then the Na plus and Cl minus will get together to form sodium chloride, right, NaCl. And we're crisscrossing charges every time here. So what's weird is that this acid and base, despite it not having OH in it, it's still basic, can combine to make something that is a form of water. What's weird is that carbonic acid actually secondarily breaks down to form water and carbon dioxide. So the generic formula of acid plus base yields salt and water is incredibly generic. It's a good guide, but it's not always going to follow through. But this for sure is our salt, and this is like our water in a sense because it continues to break down. So don't try to force everything into the cookie cutter of acid plus base yields salt and water. Just do the double replacement and then let's go with it. Yeah.
It's not over to write the acid or base first.
It does not. Now I do need it. Do I need to balance this? Is it good? It looks good to me too. The H's, there's 2 H's, there's 2 H's, we're good. All right, Bradley, what's nitric acid?
H3.
That is not hydronitric acid. This is a not binary one. Ask your table, let's go, I'll come back to you in a second. Front table up here, give me magnesium hydroxide. MgOH2 like this. Parentheses, thank you. Okay, Bradley table?
You don't have H.
You do have an answer. Not acceptable. Let's go. H.
H.
HNO3. Nitrite or nitric is coming from nitrate. Nitrate is NO3. Crisscross 1 and 1. Okay. Kaylin's table. Give me one of these products. So Mg is our cation, and what'd you say? So NO3 is nitrate, right? Nitrate has a negative charge. Mg and NO3 come together to make Mg and O3 like this. Where's the 2 coming from? Right, so you're crisscrossing charges every time. So magnesium is a 2 plus charge. You crisscross it over. Nitrate has a 1 minus charge. Crisscross it over. We're good here. Meredith's area. Tell me the last product. HOH, right? The plus from the H plus, OH minus makes HOH. All right, we got to balance this, guys. Frank, got me?
2, 1, 2, 1.
2 on this one. Ooh. 2 here, 1 here, 2 here.
Oh,
Not that one.
that's
Right.
not the way I read it. So
Oh.
2, 2, 1, 1, 2 on that.
Got you. Thanks. Good. So we had the need for 2 nitrates. We need to put a 2 coefficient there, and we had 2 hydroxides here, and that 2 H's there makes 2 waters overall. So we had to put a 2 over here for the 2 waters. Okay. All right. So making sure you're focusing on crisscrossing charges, identifying ions, reviewing your acid nomenclature. Acid nomenclature is one we'll keep on working on. That's a neutralization process. Now, what you guys just did in your lab was the opposite of that, which we call hydrolysis. So the word hydrolysis, you guys know what lysis stands for? Splitting. Like, you guys did hydrolysis, no. Oh, was it hydrolysis? It was photolysis, right? Okay. You guys did photolysis in biology. Lysis means to break or to split. You can kind of think of it almost like Lysol. What's the job of Lysol? Do not say to clean. It actually bursts open bacterial cells and it kills them that way. So it breaks open their cell walls. It's a tragic thing on your counter. Okay, so hydro refers to, in this case, water. So water is doing some splitting. It's doing some breaking apart. Of what? What's water breaking apart? The salt, right? It's like, hey, cation, you come with me. Hey, anion, you come with me. We're gonna make new products. Okay, so this is still a double replacement reaction. It's just reverse what we just did. So let's do 2 of these. Notice how I'm not gonna say salt plus water yields blank. I'm gonna say, what's the reaction for the hydrolysis of X? So I'm gonna say the word hydrolysis there. So I want you to hydrolyze this and that, and we're good. Do those 2 reactions in your book. So you're writing the hydrolysis of these salts. Try to refrain from using your polyatomic ion list unless you absolutely need to. You should still have those in your brain. You cannot always depend that you'll have those in your brain. Make sure you're crossing your charges every single time. Decomposition has 1 reactant within almost products. This still has 2 All right, Will, your front table, little area up here, can you guys tell me calcium phosphate? Ca is calcium, and phosphate separately is PO4, but we have to crisscross charges, and what are those? So, where's that 3 going? So, where's this 3 coming from? Phosphate's charge crisscrossing, and then what about over here? 2. Ca3, parentheses, PO4, parentheses, 2. That is calcium phosphate. Thumbs up if you got that. Very few of us. That is sad. You need to be crisscrossing your charges. This is old news to you, okay? Hydrolysis means to add water. I'm going to write it as HOH because I just think that's a lot easier for you guys. Okay, Mikado, pick up from there. Give me one of the products. Okay, so you're putting calcium with a plus because it has a 2+ charge. You're crisscrossing it with hydroxide with its negative charge to give me CaOH parentheses 2. Where's this 2 coming from again? Calcium's charge. William, give me the other product.
I got H3.
Wonderful. So where's this 3 coming from right here? Right, because you're taking the plus, the cation, the H plus here, and you're blending or crisscrossing with the negatively charged phosphate, and you still crisscross charges every single time. And that's going to give you, what's the name of that, William? Phosphoric acid, yes. Okay, and then Frank balance.
I got 1,
Okay.
6, 3, 2.
We're good here for sure?
Yeah, I was making sure that's
Okay, so in the case of making sure you're balanced, the only thing you really need to notice is that your subscripts are kind of getting crazy here. So we have 2 hydroxides, we only had 1 there, but we have 3 hydrogens and we only had 1 there. So the only way you can make 2 equal 3 is by doing the least common multiple, which would be 6, which is why Frank put a 6 in front of here. So upon making 6 hydrogens, you had to put a 2 in front of the acid, and then because you had 6 hydroxide, you had to put a 3 in front of calcium hydroxide, and then everything else panned out. Okay? Next one, Bradley's table, lithium nitrate. Li NO3. So lithium and then nitrate. I'm going to put a parentheses around nitrate so you can see that very clearly. Ashton's table, after I write water, sorry, we're doing hydrolysis, we're adding water. Ashton's table, tell me one of the products. Lithium hydroxide, LiOH, thank you. And then somebody else at that table, tell me the other product. H and then NO3, good. And so in this one, all these charges were what? 1s, right? 1 pluses or 1 minuses, that's why we had no additional subscripts to deal with. Therefore, we actually don't have any additional balancing to do either. So the lithium cation and the hydroxide anion got together, and then the plus from this H right here, and the nitrate got together. It's still double replacement all the way. Now, here's the beauty of looking at these and then remembering which ones are strong acids and strong bases. We can determine the I'll say pH kind of the salt based on what parent acids and bases that previously made them. So basically, I'm going to look at this last one. When I'm looking at this, if I reverse this process, what kind of reaction is that? Neutralization. And going the forward, it's hydrolysis. So we know that they're just reversed of each other. So technically, who made baby salt over here? Who made lithium hydroxide or lithium nitrate? Mama lithium hydroxide and daddy nitric acid, right? So you know, like you have characteristics from your parents, right? Genetics, you got different traits, heterozygous and homozygous. And you might look, who looks more like their mom? Like I certainly do. Who looks more like their dad? Okay, so some traits are stronger and they kind of push that characteristic to be more predominant within you. Same thing happens with baby salt over here. So looking at baby salt, we actually have a mom and a dad, and I'm going to go with me on this analogy here. But you're going to tell me their strengths. So looking at this base, is this a strong base or a weak base? Loud and proud. How do you know it's strong? It's in the little b, right? It's one of the 8 strong bases because you have that memorized. It's not going to say, hey, I'm strong. You have this memorized. Okay? So what about this one? This is an acid, right? Is it a strong or weak acid? I see some of us flipping through our books because we don't have them memorized yet. Flip through your book. Don't neglect that. Okay, and you know that because you have it memorized. You know your 6 strong acids. So, because both of these are strong acid or strong and strong, so strong bases and strong acids, this salt, when I test the pH of it, it's going to not be either one. It's not going to be a basic or acidic. It's going to be neutral because neither of the traits one over the other. So, what would yield a basic salt? What combination of parents? So strong what? Base and weak. And how would you know it's a weak acid? It's not one of the 6 strong ones. Okay? So let's go back up here. This baby salt, calcium phosphate, came from mama calcium hydroxide and daddy phosphoric acid. So let's go with that same theme. This is a base. What kind of base? Because it's one of the 8 in the B there, okay? And then what about this one? It is, why is it weak? Because it's not strong, okay? So which characteristic would this salt take on? It would be basic. So what color would it turn red litmus paper? Blue. What color would it turn blue litmus paper? It would stay blue. That's why we just did that lab. I need you to you're going to kind of keep that in your mind. You'll finish up the analysis on that shortly. Okay, so other things I need to clear up with you guys. I think we all know the pH scale, right? Goes from what to what? 0 to 14. Now, do you understand what's happening? And I would write this down someplace, either extra notes or on the back of your lab, whatever it is you need to do. I'm going to clear up some things and make sure you know what you're talking about in your problem set. So, if I'm looking at 0 to 14, what's happening to hydronium ion as I go from left to right? Tell me if it's going up or tell me if it's going down in concentration. Make a choice. So as I go from 0 pH to 14 pH, what's happening to the hydronium concentration? You got to give me some thumbs. I got to see some commitment here. A lot of us are saying down. Why? Yeah, hydronium represents something that is acidic. So you're going to have a high concentration of hydronium over here. And then as you go, it's going to decrease. And you'll have a low concentration of hydronium over here. Well, opposite of that, we know that, remember, they complete each other, hydroxide and hydronium. They always, when you multiply their concentrations, they always equal what? 1 times 10 to the negative 14. So they have to complete each other. So if I have a high concentration of hydronium over here, what do I have of hydroxide over here? A low concentration, because it's towards the more acidic realm, right? We're not going to have a lot of hydroxide. What about over here? Yeah, we're going to have a high amount of hydroxide because it's more basic, and we should have more hydroxide than we have hydronium. Remember, they complete each other. So that's one thing to keep in mind. You should know which ion is associated with acids and bases. All right, give me 3 pH formulas. Talk in your groups first. You have 30 seconds. Do not look at your notes, like I said. All right, pause. Will, give me one. pH plus POH. pH plus POH is equal to 14. John, give me another. Hydronium equals 10 to the negative. What's hydronium representing? No. pH, right. Hydronium is representing H plus, and H plus and pH are the basically always used together. Kaylin, give me one more. Negative log of what? OH concentration. Marvelous. You should have at least 3 of them memorized because you have used them so frequently, especially in your problem sets. When I give you a quiz, you will not have the pH formulas in front of you. You should have realized the relationships, especially the logarithmic ones. What does bracket mean, everybody? What means molarity? It means concentration, okay? So it means molarity. That's why we keep putting things in brackets so that you're familiar with that. I need an example of a conjugate acid-base pair. Yeah. Yes. Well, concentration is a generic word because I can express it in percents or molality, molarity, and some others. So, but specifically, it does mean molarity. All right. So, an acid-base pair, but it's a conjugate acid-base pair. Think for a couple more seconds. Talk in your groups if you need to. I'll need one example. All right, Caleb's table. I'm ready when you are.
Alright, we said H plus, or hydrogen chloride would be H plus and Cl negative, right?
Okay, so HCl and Cl minus, is that what you said?
Yeah, right?
Hydrochloric acid? Sorry, you said hydrogen chloride, I wasn't sure what you were saying. All right, so this would be considered the what?
The acid
And this would be considered its what?
base.
Its conjugate base. Because what's the only difference between an acid and its conjugate base?
This is
A single H plus. You see the main difference is a single H plus. Let's get another volunteer on this one. Or I can give us one too, yeah.
Like acetic acid.
Okay, so acetic acid C2H3O2. C2H3O2. 1 minus. Again, different by 1 H plus. Now, if those were acids to conjugate bases, I'll do a second one like this. Actually, I'm going to give you methylamine, which is the precursor to meth. Okay, that's methylamine. That's a base. It's actually a weak base, but it's a base. Give me its conjugate acid. CH what? This is actually like a more of that's kind of like hydrocarbon group. These generally don't get changed a lot. It's the more electronegative action that happen. So CH3, NH. No, what do bases do? H3 what? Plus, because when you gain an H, it's not just an H, it's an H plus. Okay, so that would be a good conjugate acid because it has an additional H group with a plus charge as well. So you're just going to be thinking about how it's acting and then adding an H or subtracting one. All right, so these terms, mono, di, and tri, product, that was one example on your reading or on your true false, so I'm going to go over that shortly. But what do you guys think that means? 1, 2, and 3 what? Hydrogens, yes, because protic means, remember, that means hydrogens essentially. So everybody give me an example of give me a monoprotic acid. HCl. Give me a diprotic acid. H2CO3. Give me a triprotic acid. H3PO4. The list goes on and on. We could do that over and over again, but you're looking for 1 H, 2 H's, or 3 H's. That's it. What color does phenolphthalein turn? Ashton, what do you guys this in your group? What color does phenolphthalein turn? Pink. At what pH? Any takers? Okay, you should know this one as well. It's going to turn pink in acidic or basic conditions. You guys have your indicator notes. Basic pH, and I told you guys yesterday, different forms of indicators turn at different pHs. This turns at pH approximately 9. Oops. And I showed you that big chart of indicators, and they had all kinds of different color changes. This one changes at approximately pH 9. Litmus paper, we already know that one pretty well, I think. Now, this was question 13. Was this the weak acid question, or was this question 13? Okay. So this is the one I knew I needed to go over because we were focusing on strong for so long. Now we're just going to look a little bit deeper into weak. So we cannot do pH equals negative log of H plus to find the pH of a weak acid. We cannot do that because what we do is when I give you an acid, let's say I give you like 0.15 molar nitric acid, you're making the assumption that this is also the molarity of what? Because you can't plug nitric acid in here because that's not a nitric acid. So what are you assuming this concentration is also of? It's not a secret. You've been doing this. Say again? Hydronium or H plus, right? You're assuming that 0.15 molar is the concentration of H plus or hydronium. As remember we can make those interchangeable because HNO3 is it is an acid. What kind of acid? It's a strong acid. So you're making this assumption that the concentration of the ions it creates is the same as the parent of the original because it 100% ionizes, right? So because nitric acid does 100% ionize or dissociate, we can make that assumption. That's fine. That's why we are able to do pHs like this with our strong stuff. But because we have something weak like HC2H3O2, which is what again? Acetic acid, right? It doesn't do that 100%. So I cannot make the assumption if I give you 0.15 molar of this, I cannot just take that and go, yeah, let's just plug that back in there and find the pH. So we actually have to do something much more complex. It's a little bit more advanced, and we'll get into it in about a week. But we actually have to set up something called an ice box. So we take the acid, which is the weak acid. We could do the same thing for a weak base. We add it to water. We do the double-headed arrow, which means what? It can go in reverse, and it doesn't 100% go in the forward direction. Make this act as an acid. What happens? Acids do what? Donate when they make hydronium many times, left over acetate, okay? So what we do is we set up something called an ice box. We write initial concentration, we look for the changes that occur, and then we look for equilibrium conditions. And then at the equilibrium conditions, we take this information and we plug it in a Ka expression. Ka is something that's going to give us information about how weak an acid is. It's just a value, and the value is either really low or somewhat low, but it's still going to be a lower value. That's why I said I want to get into that a little bit later, because I think our brains are fairly saturated. Okay, so just know it's a totally different process. Cool? A couple of you guys need to finish some more of your PS. Can I take a question on PS? Because I know that some of you guys left some blank. If not, if you don't need questions from me on PS, look at the hydrolysis lab you were working on and quietly work on that while I take a couple of questions. Yeah, you're going to do it 3 times. Yeah. Awesome. Speak now, yeah. Can you tell me what that is? Oh, we're just going to and then use that hydronium times hydroxide. You also can check your true false. I'll leave this up here for a minute while you guys are asking me questions. Check your true false. Check your true false, and then let's talk about a couple of those. Quickly, please. Yeah. Jacob, that's what you're doing, right?
Yeah, well, I was not sure. Don't you have to divide by anti-log?
No, because anti-log is actually not. So the only thing you ever divide by, like, you always do an opposite function. Maybe I find it I have one more thing I have to talk to you guys about. All right, guys, I'm giving you a couple minutes to keep addressing anything on your lab, and then I'm going to make sure I talk one more thing to you. Tell you guys one more thing. I got about 10 minutes left. Raise your hand if you're already done with your lab. Oh, great. Okay, keep working. If you are done, you can put it in the box. Isabel, I'm gonna get back to you after this talk tomorrow.
Yeah, put it in the box, Jake.
Alright, guys, you should be getting close to done with your lab. Take a couple more minutes. We're gonna go in the box before you leave.
I feel like I'm a third.
Jacob, focus on writing on that versus cutting it, because you're turning that in.
Okay.
You can start on PS19B. If you get done with your lab just a little early, begin 19B, you can do like the first half.